Hello everyone. So today I am starting the very last chapter that we have in our course, and that is chapter 14 of the textbook. So in chapter 14 we are discussing about gas vapor mixture and air conditioning. Okay. Now whenever the temperature of the gas is below the critical temperature, the gas phase is called the vapor. Okay, so the vapor case is the case that the temperature is below the critical temperature. Also, whenever we are discussing about the vapor, chances are that we have a phase change, we have the condensation, because that vapor can be close to the saturation temperature. All right, so in this chapter we are discussing about the cases that we have a combination of gas and vapor. Okay, so in chapter 14 we are discussing today, we have gas vapor mixtures. Okay, at temperatures below the critical temperature TCR, gas phase of a substance is called vapor. All right. Okay. Now, as I said, the term vapor means that the gaseous state is close to the saturation. So let me just write this down. The term vapor means the gaseous state that is close to the saturation saturation region of the substance. Okay, so because of this, because we are close to the saturation region of the substance, there is possibility of condensation. There is a possibility of condensation. Okay, so that means chances are that the vapor condenses to liquid. So in chapter 13, in the previous chapter, the temperature that we had was above the critical temperature. But in this chapter, chapter 14, we are discussing when the temperature is below the critical temperature. Okay, so in gas vapor mixtures, which is basically what we are studying in chapter 14, the vapor may condense out of the mixture, forming a two-phase mixture. All right, so let me explain this bullet item. Imagine that we have a mixture of gas and vapor. All right, so right now, whenever we have this mixture, the phase is still 100% in gas phase because vapor is still a gas. All right, but the thing is, vapor is close to the saturation. So whenever that vapor condenses, okay, by doing that condensation, we will have a liquid phase. So think about this. We have gas phase, we have liquid phase, which is the condensed vapor, and because of that we will have two-phase mixture of gas and liquid. Okay. On a separate note, in the course that I would like to develop, we don't really know when, but maybe in spring 2021, we are going to discuss about liquid gas two-phase flow, two-phase flow basically. All right, now speaking of air, in this chapter, in chapter 14, we are discussing about air a lot. All right, so air itself, you should know that air is a mixture of nitrogen, oxygen. So the majority of air is the nitrogen and oxygen part or components, but there are also some other gases or some other components. But the majority of air, the majority of the components are nitrogen and oxygen. It's around 79% of air nitrogen and around 21% oxygen. Very small amount is other gases that we have in air. And by the way, the tables that we have for air in our textbook, that is for dry air, and I will explain what that dry air means in today's lecture. Obviously, air in atmosphere can contain some water vapor. So let's say air in atmosphere contains some water vapor and is referred to as atmospheric air. Okay, so the air that we have in the room, that is in fact atmospheric air. That's a definition. Okay, so the atmospheric air simply means the air, which is nitrogen and oxygen, and water vapor, because here you do not see any water vapor in these two combinations. But in addition to these two, we have water vapor in the air, and that is the air that we are breathing. So that is the atmospheric air. Okay, now the air that does not have any water vapor is called dry air. Okay, you cannot find this dry air in room. The air that you find in room, the air that right now I'm breathing, the air that you are breathing right now, that is not dry air. Okay, I will explain how you can find dry air, but let me just write down the bullet item. So air that contains no water vapor is called dry air. Okay, now, as I said, dry air is not something that we have in the room. So the air that we have in the room is atmospheric air simply because it has water vapor. Now, in case you're wondering where is this dry air, this dry air is in fact in labs. In those air bottles that we purchase, there is no moisture content in those bottles. So that is dry air. The tables that you have been using so far, let's say the table at the end of the textbook, I think A17 or 18, that is for dry air. Let me give you the exact table number because you have used that table. A17. Okay, I'm not sure if you remember this table, but we used A17 before, right? It says ideal gas properties of air. The properties that are listed here, they are properties of dry air. There is no moisture in it, okay? But we can add moisture based on the equation that we have, okay? So to get back to my question, this dry air is not something we have in the room. If you need that, then for some reason, for research application, let's say, so they are in gas bottles that we can purchase. Okay, so atmospheric air can be treated as an ideal gas. The reason behind that is because air and water vapor are behaving ideally. Okay, so atmospheric air includes air and water vapor. Okay, this thing here, atmospheric air includes air and water vapor. So let's say dry air plus water vapor. Because dry air and water vapor are both behaving ideally or are behaving as an ideal gas in the room temperature and pressure, then we can say that the atmospheric air is also behaving as an ideal gas. So the bullet item is atmospheric air can be treated as an ideal gas since dry air and water vapor are both behaving ideally. So you remember earlier we mentioned that if a gas mixture has components, that the components are behaving ideally, then the mixture is also behaving as an ideal gas. This is exactly what we have here. Atmospheric air has dry air in it and it has water vapor in it. Both of these two components, let's say this is component 1 and this is component 2, both of them are behaving as an ideal gas. So their mixture is also behaving as an ideal gas. All right. Not to mention that the dry air itself is also a mixture of nitrogen and oxygen. So here we already have a mixture. So atmospheric air is a mixture of a mixture basically, and also another gas. Okay, so the other thing is about the pressure. Okay, so the pressure of atmospheric air can be equal to the pressure of dry air plus the vapor pressure. So this P is the atmospheric pressure. Subscript A is for dry air. So PA is pressure of dry air, and PV is pressure of water vapor. Okay, so this P that we have here can be the atmospheric pressure. So the atmospheric pressure is sum of the dry air pressure and water vapor pressure. So the other name for this is vapor pressure. So this PV, other name for that, you may see that in the problem, when they say vapor pressure, they are referring to this PV. Okay, now the question is, what is the physical meaning of vapor pressure? Like, what does this PV mean? The answer is very simple. So question is, what is the physical meaning of vapor? Okay, so what does PV mean? So the vapor pressure, or PV, simply means the pressure that the water vapor would apply on the container if that is alone within the tank. Okay, so let's say the answer is the pressure that water vapor would apply on the interior wall of the tank if that is the only component in the tank at the temperature and volume of the atmospheric pressure. I'm sorry, of the atmospheric air. Now there are some definitions that we have in this chapter. So one of the definitions that we have is the absolute humidity. Okay, so absolute humidity, there is also other names for that. Another name that we have for absolute humidity is specific humidity. Okay, so the absolute humidity or the specific humidity describes the amount of water vapor we have in air. Okay, so we show that with omega, and omega is equal to mass of vapor over mass of dry air. Okay, and the unit here is very important. The unit is kilogram water, let's say kilogram water vapor per kilogram dry air. All right, the unit is mass of vapor per each 1 kilogram mass of dry air. Now, depending on the tables or the charts that we use, sometimes in the charts they have gram water vapor per kilogram dry air. The reason is MV is much smaller than MA. In atmospheric air that we have, the mass of dry air is much greater than the mass of water vapor. So you know that subscript A is for dry air. That means MA is mass of dry air and MV is mass of water vapor. A very good review question at this time is, what is dry air? So dry air is air without any water vapor. So dry air itself is the mixture of nitrogen, oxygen, and some other gases, but the majority of it is just nitrogen and oxygen. You do not see any water vapor here, and that forms our dry air. But dry air is different from atmospheric air. Okay, now I can expand these equations, these masses, these m's that I have based on the ideal gas law. So I can say the absolute humidity, which is equal to mv over ma, I can write these masses based on the ideal gas law, right? Because on a side note, you know that P, pressure multiplied by specific volume, is equal to RT. This is the ideal gas law. And because that is specific volume, it means this V is volume divided by mass. So I can say pressure multiplied by volume. So this is capital V, this is volume, but over M, mass, is equal to RT. All right. Once again, this V is a specific volume, but this V is just volume. And here we have M. Now, if I solve this equation for M, which is mass, then M is going to be pressure multiplied by volume over RT. R is the gas constant and T is the temperature. And this is exactly what I'm going to use here. For this M, I'm going to use PV over RT. So MV is pressure of vapor. Be careful with the subscripts, they are very important. So pressure of vapor multiplied by volume over R, or the gas constant of the vapor, multiplied by temperature, PV over RT, PV over RT, and obviously this V is volume. Now here I do the same thing, but the subscript instead of V are going to be A for dry air, right? Pressure of dry air, volume over R, gas constant of dry air, temperature. All right. Now, you know what? The volumes are the same, so I can cancel this volume with this volume. Likewise, the temperatures are also the same. So that means I will end up with PV over RV over PA over RA. Okay, so this RV is the gas constant of water vapor. All right, if you go to table A1, you can get the value of this RV. Same thing here, this RA is gas constant of air. So also this one comes from table A1. So these two properties, they are both coming from A1. Now the question is, if you go to A1, if you're looking for RV, you need to know that this R is R for water. So you go to table A1, if you have water or steam, then R is what you want to get from that table. Let me show you here. Okay, you see this table? We use it many times. So here you want to find this water, and this is the properties of gases. Okay, this is the gas constant. That means the R that you read here, this 0.4615, whatever the unit is R value for water vapor. All right. So long story short, both of these two R's are coming from A1. So PV over 0.4615 kilojoule per kilogram Kelvin over PA. Now this is RA from the same table, 0.287 kilojoule per kilogram Kelvin. If you do the math, if you just do the math between these two, you will see that you have 0.622 PV over PA. All right, this simply means that the absolute humidity is equal to 0.622 PV over PA. Okay, now there is a tendency always to replace the dry air pressure with P total minus PV, because previously on the previous page you learned that the total pressure or the atmospheric pressure is equal to PA plus PV. So I can find PA based on the total pressure minus the vapor pressure. Okay, so we tend to replace this PA with P minus PV. So the equation that you will see and use most of the time is omega is equal to 0.622 PV over the total pressure minus the vapor pressure. We are using this equation a lot. So this is the absolute humidity or specific humidity, which is based on the pressure. And once again, the unit is mass of water vapor per mass of dry air. Okay, now consider we have a container like this, right? And what we have in this container is 1 kilogram of dry air. So let's say within this container we have 1 kilogram of dry air, right? And let's say at the very beginning there is no water vapor. Okay, water vapor content is equal to 0. All right, so these two numbers, this 1 kilogram of dry air and 0 mass of water vapor, obviously gives us an absolute humidity mv over ma of 0. Okay, simply because mv is equal to 0 and ma is 1, it can be any number, but as long as mv is equal to 0, that omega is equal to 0. Now let's add some water vapor into this tank. So let's say let's add some water vapor to the tank. Now what we are going to do, we are increasing mv. So mv was initially 0. This thing here means mv is equal to 0. But now we are increasing mv. So guess what? That absolute humidity is also increasing. All right, so we are increasing this absolute humidity until the air cannot hold any more moisture. Okay, so let's say by adding water vapor to the tank, the absolute humidity increases until air cannot hold more moisture. Okay, so that air that cannot hold any more moisture is called saturated air. So this air is called saturated air. And saturated air is the air that by adding any more moisture, the moisture will condense. Okay, so any moisture added will condense, and that is the definition of saturated air. Okay, basically the air has reached to its limit of holding moisture. Now the question is, How to calculate the amount of water vapor in saturated air? Question. How to calculate the amount of water vapor in saturated air? That's the question. One thing we can do, we can use this equation that we had before, but by simply replacing P, which was initially the total pressure, with PG. Okay, so let's say replacing P, or the total pressure, with PG, and I will explain that what PG is in equation omega equal to 0.622 PV. This time we have PG minus PV. This PG is the saturation or the saturated pressure of water at the temperature of T. So this PG is P sat of water at temperature of T. Okay, and you will see how this thing works in an example problem. But by using this equation, we can find the absolute humidity. Okay, now the first definition that we had was about the absolute humidity or humidity ratio. So the absolute humidity is one way to describe the moisture content that we have in atmospheric air. There is another definition to describe this MV. Okay, it's again another ratio, but instead of mg in the denominator, instead of ma in the denominator, we are going to have another property. So let's say the second way to describe the moisture content in air is called the relative humidity. Okay, so the relative humidity is defined as the amount of moisture that air holds, let's say MV, relative to the maximum amount of moisture that air can hold at the same temperature. Okay, so we show this relative humidity with this letter. Let's say phi is equal to mv over mg. mv is the moisture content that we had before. mg is the maximum amount of moisture that air can hold at a given temperature. All right? So once again, I'm going to use the ideal gas law as we did before, and I'm going to rewrite PV based on pressure of vapor over volume, multiplied by volume over R, the gas constant of vapor, multiplied by the temperature. So I just replaced mass by this, and this is coming from the ideal gas law. And instead of mg, I do the same thing, but the subscript is going to be pg, and that's it. So pgv over rvt, because don't forget that both of them are mass of vapor. This is the mass of vapor we have in the system. This is the maximum possible amount of moisture that air can hold. But substance-wise, they are both for water. Okay, so this time I can cancel V with V, T with T, and also R with R. So I end up with PV over PG. That means my relative humidity is equal to PV, vapor pressure, over PG, and PG is in fact Psat at that temperature. So this is equal to the saturation pressure at the temperature. Okay, now there are two equations that correlate the absolute humidity with relative humidity. So one equation is phi is equal to absolute humidity multiplied by pressure over 0.622 plus omega multiplied by Pg. That's one equation. The other equation is omega is equal to 0.622 phi Pg, pressure, total pressure minus phi Pg. And these two equations are in fact the same. We use this one if we want to solve for relative humidity, and we use this one if we want to solve for absolute humidity. Okay, the amount of dry air in the air-water mixture remains constant, right? What about the enthalpy? The enthalpy of atmospheric air is expressed per unit mass of dry air. So let me just write these two bullet items. So the amount of dry air in the air-water vapor mixture remains constant. So that means if there is anything changing, that is the amount of water vapor mixture by condensation, or even adding more into the vapor. Like this portion, the dry air portion is fixed, but this portion can change. Also, we have a bullet item about the enthalpy. The enthalpy of atmospheric air is expressed per unit mass of dry air. That means if we are looking at H being equal to H of dry air plus H of water vapor, then this HA, or H of dry air, is mass of dry air multiplied by mass enthalpy of dry air plus mass of vapor multiplied by H of V. Okay, now I can divide sides by mass of air, and that will give me lowercase h is equal to h over mass of dry air. Okay, so basically I'm dividing the right hand side by ma. So the first term is just going to be ha, the second term is going to be mv over ma, hv. And guess what? mv over ma is in fact our omega. We had this before. So that means H is equal to HA plus omega Hg. So subscript vapor changes to G, and this H is enthalpy of atmospheric air. So this is the enthalpy of air, but not just dry air, but dry air and water vapor. This term is enthalpy of dry air. What is this Hg? Hg is the enthalpy of water vapor evaluated at a certain temperature. So you go to water saturation tables and you find Hg based on the temperature. All right, so this Hg is kilojoule per kilogram. The entire unit for this is kilojoule per kilogram of dry air, right? So the unit here is coming from dry air. So this Hg is kilojoule per kilogram, but this is coming from water table. But the entire unit for this equation, or let's say unit of H, let me say unit of H is kilojoule per kilogram of dry air. Okay, now we are going to do one example and you will see how these equations work and how we can use them. So in the example that we are going to solve, we are going to find the mass of dry air and water vapor. So the question says calculate the masses of dry air and water vapor in 90 meter cube in a 90 meter cube room at 93 kPa, 26 degrees C, and 50% relative humidity. Okay, so this RH is the relative humidity. All right, so in this problem, what we have is a room, and in this room, the volume of the room is a 90 meter cube. So let's say that this cube shows the room. The volume is 90 meter cube. The temperature of atmospheric air in this room is 26 degrees C, and the relative humidity is 50%. Also, the atmospheric pressure is 93 kPa. You know what? It's really important in problems like these. It is very important to understand what is the given pressure, like, or what pressures we have. The question is, this 93 kPa, is this PA or PV or just P? The answer is this is only P. Okay, so between these three, we need to figure out which one it is. Is this PA or PV or PA plus PV? It's really important to know what that is, and that is PA plus PV. The reason I say that is because the problem statement didn't really say that the dry air pressure is like this much. If the problem statement says the dry air pressure, then that pressure is PA, all right? But right now, because the problem statement says nothing, then this means this is the atmospheric pressure, which is PA plus PV. By the way, these are not negative sign. They are just bullet items. Like, I just wanted to ask which one it is. It is PA plus PV. All right, so you know what I'm going to do? I'm going to use the equation we had for absolute humidity. I'm going to start with this equation. Omega is equal to 0.622 phi pg over p minus phi pg. Okay, now one more thing. Getting back into this question, in the notations or the equations that we have, we show atmospheric pressure with P alone. Some textbooks show that with P subscript T standing for P total or P ATM or atmospheric pressure. I just follow the convention we have in the textbook. So whenever we have just P, then that means that is the atmospheric pressure. So here, this P is the same as this one, which we have it already here. So in this equation, this is what we have. This is given in the problem, 93 kPa. This is the relative humidity, which is 50% or 0.5. So this is also known. Pg is coming from the temperature. So Pg is in fact P sat at 26 degrees C. Okay, so you go to the table and you find PG at 26 degrees C, and that is 3.37 kPa. So that means this is also checked. This is also checked. This is also checked. So I can utilize this equation to find omega, right? So that gives me omega is equal to 0.622 multiplied by, instead of this relative humidity, I do 0.5 multiplied by Pg. This is coming from table. This is from water table, by the way. Over P, which is this one here, or given 93 kPa, minus the relative humidity, which is 0.5, minus Pg, 3.37 kPa. So if you do the math, you will end up with omega equal to 0.01147 kilogram water. Let me just write it here because the unit is very important. So this one has the unit of kilogram water vapor over kilogram of dry air. That is, this thing is the unit of this number. What does it mean? It simply means in this room, for each 1 kilogram of dry air, we have 0.01147 kilogram of water vapor within the room. It's really important to understand that this number is for each 1 kilogram of dry air. It does not mean that this is within the 1 kilogram of dry air. This means that for each 1 kilogram of dry air, there is 0.01147 kilogram of water vapor. Be careful that here it is for. It does not say in each 1 kilogram of dry air there is this much. That will be wrong. Here it says for each 1 kilogram of dry air there is this much kilogram of water vapor. Here we have 4. All right, so let's move on. What I'm going to do, I'm going to utilize pretty much the same number, the same value, and based on that, I'm going to obtain the vapor pressure by another equation that we have. So the other equation we had was omega is equal to 0.622 PV over P minus PV. We had this equation before, right? So here in this equation, the left-hand side is known. It's right here. This P is also known. This is the given pressure, which is 93 kPa. So the only unknown that I have is PV. So I can solve for PV. Omega is 0.01147 kilogram H2O or water vapor or over kilogram dry air is equal to 0.622 PV, right? 93 kPa minus PV. So PV is the unknown here. So you can solve this for PV, and that gives you PV or vapor pressure of 1.68 kPa. Right? Now, you remember I said that the total pressure is the vapor pressure plus dry air pressure. Now think about this. The total pressure in this problem is 93 kPa. The vapor pressure is 1.68 kPa. So based on that, we can find the dry air pressure. PA is dry air pressure, which is 91.3 kPa. Okay. Now, we were looking for mass of dry air and mass of water vapor. What I'm going to do, I'm going to utilize these two pressures. I'm going to utilize them in the ideal gas law, and based on that, I'm going to find mass. Before mass, I'm going to find the specific volume, and based on the specific volume and based on the given volume, I'm going to find mass. Right? So let's say for dry air, I would say pressure of dry air, specific volume of dry air is equal to gas constant of dry air, the temperature. PV equal to RT. What is this V again? This is a specific volume. All right. PA, I know the value of PA. 91.3 kPa multiplied by specific volume is equal to RA, gas constant for air. Table A1, 0.287 kilojoule per kilogram Kelvin multiplied by T. T is 26 degrees C, but you know that this temperature should be in Kelvin. All right, so you convert the temperature into Kelvin, and that will be 299 Kelvin. So this gives you the specific volume for dry air, and that is 0.939 meter cube per kilogram. Now, because we have the volume of the room, and that volume is equal to 90 meter cube, I'm going to utilize these two numbers to find mass of air. So M dry air is, let's say, volume divided by this. 90 meter cube divided by 0.939 meter cube per kilogram. If you are wondering why did I do like this, like why this ratio gives me the mass, just look at the unit. Here I have meter cube, here I have meter cube per kilogram. So this meter cube cancels this meter cube, and the kilogram goes on top. So M is going to be 95.8 kilogram dry air. So in this room, the mass of dry air that we have is 95.8 kilogram. So let's do for water vapor. Pretty much the same thing. This time, pressure of vapor multiplied by a specific volume of vapor is equal to R of vapor multiplied by temperature. All right, the pressure of vapor, we have it, 1.68. The vapor I'm looking for is RV. This is the gas constant of water, table A1, 0.4615 kilojoule kilogram Kelvin multiplied by temperature, 299 Kelvin. That gives you the specific volume for vapor equal to 82.13 meter cube per kilogram. All right, and that gives you mass of water equal to 1.1 kilogram. So in this room we have 1.1 kilogram of water vapor, and we have 95.8 kilogram of dry air. This is what we have in this room. So these two are the answers. Now, we are done with the solution or the answer for this problem. What I would like to do is just work with these two numbers. All right. I'm going to find the ratio of MV over MA. MV is 1.1 kilogram. MA is 95.8 kilogram. All right. So if you do that, let me put it in my computer. In my calculator. So 1.1 divided by 95.8, I got 0.01148. The question I have for you is about MV over MA. Does it look familiar or similar to you? Didn't we say that MV over MA is omega, or absolute humidity? So here, this ratio is this much, and the unit is going to be kilogram of water vapor over kilogram dry air. And you can confirm this number with this number. Like these two are exactly the same. All right. So this is just one way of checking our solution. Trying to show these two together. Like this number is the same as this number. This is the omega over absolute humidity. This is also omega because this is MV over MA. The MV and MA that we found during this problem. Now let's see how the relative humidity changes with temperature. And in order to do that, I'm going to do a very simple example. So imagine that we have a tank, and within this tank the water vapor is 2 kPa. So let's say water vapor pressure in a tank is 2 kPa, right? The question is asking for calculate the relative humidity. RH is the relative humidity inside the container at three different temperatures. Temperature of 60 degrees C, 40 degrees C, and 20 degrees C. All right, so what we want to find the relative humidity in this tank for three different temperatures. So let's say this is our tank, and let's say these are the water vapor molecules. We know that in all three temperatures, PV is equal to 2 kPa. And let me start with 60 degrees C. So at 60 degrees C, the relative humidity is equal to PV over PG, right? PV is given at 2 kPa, so it's a fixed number, but PG is in fact Psat at given temperature. Psat at 60 degrees C. So that means my relative humidity is 2 kPa. Then you go to table for water tables and you obtain Psat for 60 degrees C, and that is equal to 19.94 kPa, and that gives us a relative humidity equal to 0.1. Okay, so this is the relative humidity when the temperature is at 60 degrees C. Let's do it for 40 degrees C. Pretty much the same thing. The relative humidity is vapor pressure over Psat. This time, Psat is evaluated at 40 degrees C, but PV is still the same. So 2 kPa here. Psat is evaluated at 40 degrees C, which is 7.38 kPa, and that gives a relative humidity of 0.27. All right. By the way, sometimes you see in the problems they are reporting the relative humidity in percentage. Then here, if you want to report it in percentage, that will be 10%. And here, if you want to report it in percentage, it's going to be 27%. So this was for 40 degrees C, and this was for 60 degrees C. Let me also do it at 20 degrees C. So you will see that the relative humidity is PV over Psat. PV is a fixed number, 2 kPa. This time Psat is evaluated at 20 degrees C. So at 20 degrees C, the saturation pressure is 2.33. And that gives a relative humidity equal to 0.85. Or if you want to report it in percentage, it's going to be 85%. Now look at this trend. As the temperature drops, the relative humidity increases. You see, I started from 60 degrees C and the lowest temperature was 20 degrees C, but here the relative humidity for 60 degrees C was 10%. The temperature dropped, the relative humidity increased. The temperature dropped, the relative humidity increased. So as the temperature drops, the relative humidity increases. That means as the temperature drops, the capacity of air to hold the moisture decreases, this relative humidity increases, it means we are reaching to the capacity of air to hold moisture. So as temperature drops, the moisture capacity of air drops. Okay, that means at lower temperatures, air has less capacity or capability to hold moisture. Okay, so after a while, the moisture content, or let's say the moisture capacity, is equal to the moisture content. Okay, that means the content of the moisture that we have becomes equal to the capacity of air to hold that moisture. Okay, then in this situation we call air as a saturated air. So we call it saturated air. Okay, so saturated air is when the relative humidity is equal to 100%, and in this condition any drop in the temperature results in condensation. Any drop in the temperature of air results in condensation of water vapor. All right, now based on this discussion we can have the definition of the dew point temperature. So dew point temperature is the temperature at which the condensation starts when the air is cooled at a constant pressure. So dew point temperature. So the dew point temperature is the temperature at which condensation starts when the air is cooled at constant pressure. Okay, so let's say for instance if I have TS diagram, let's say this is the dome that we had before, and let's say this is my constant pressure line. So this is PV constant. Okay, so on this constant pressure line, the temperature at which the condensation occurs is our dew point temperature, T subscript dP, dew point. Okay, so let's say if I start from here and if I decrease the temperature but keep the pressure constant, I can follow these until I reach to this point. At this point, any removal of heat from the mixture or from the air vapor mixture results in condensation. I follow this line. The temperature doesn't really change, but we have phase change from vapor to liquid. So this phase change temperature is called the dew point temperature. All right, the point is the pressure needs to remain constant. Now, let me ask a very basic question. The wording of the question is a little bit weird, but the concept behind it is exactly what we just studied. So the question is, does a cold soda can at 40 degrees C, at 4 degrees C, at 4 degrees C sweat in a room at 21 degrees C and 38% relative humidity. So that's the question. Now, the question statement is not a very typical thing. Let me explain what it says. So let's say we have a can, a cold can. Let's say this is the can that we have. And this can is in a room that the temperature of the room is 21 degrees C. Okay, so the surrounding temperature is at 21 degrees C. The relative humidity of the surrounding or the relative humidity of the room is also 38%. Okay, the can itself is at 4 degrees C. The question is asking whether there is any droplet of condensation which is dew basically forming on the can. All right. So those condensations are basically the dew or the change of phase from vapor to liquid. And the question is asking whether that thing happens on this can. Okay. So to answer this question, to answer whether there will be any dew or condensation on the can or not, what we want to find the dew point temperature for this room. We want to find its dew point temperature and compare that dew point temperature with the temperature of the can. If the dew point temperature is higher than this temperature, then yes, there will be condensation on the can. And the answer to this question will be yes. Okay, so long story short, we want to find the dew point temperature here. In order to find the dew point temperature, I'm starting with relative humidity. So we know that relative humidity, or I could show it with this letter, both of them are the same, is PV over PSAT. That's what we know. So the relative humidity is given at 0.38, right? PV is the vapor pressure, which I want to calculate. I want to see what is the vapor pressure in this room. And PSAT is the saturation pressure at 21 degrees C. Okay, so you go to table and that will be 2.5 kPa. So this 2.5 kPa is in fact PSAT at 21 degrees C. So that will give you the vapor pressure in this room. So the vapor pressure in the room is equal to 0.95 kPa. All right. Now that I have this vapor pressure, look at this here. I can get back into this TS diagram and consider this constant pressure curve, which has a vapor pressure of 0.95, and I can find the dew point temperature for that PV value. Okay, so the dew point temperature is in fact the saturation temperature at PV, and PV is what I found here. Okay, so what you want to do, you want to go to water table, you want to find Tsat for this pressure, and that will be T dew point is equal to 6.09 degrees C. This is coming after interpolation. All right, so that means this room has a dew point temperature of around 6 degrees C. So any temperature below this will cause condensation. But for temperatures above these, there will not be any condensation. The soda can here has a temperature of 4 degrees C, which is less than 6 degrees C. So that means the moisture content in the room will condense on the wall of the can. Okay, so the moisture, let's say the moisture content in the room will condense on the can because its temperature is less than the dew point temperature of the room. So the answer to this question, which was asking whether soda can at 4 degrees C sweats in this room? The answer is yes. There will be condensation or some sweat, as the problem statement says, in this condition. Okay, now this absolute humidity is extremely important in engineering, but the question is how can we find this absolute humidity? So the question that I'm going to answer is how do we obtain the absolute humidity? Okay. All right, so in order to do that, what we are going to do, we are going to utilize the concept of adiabatic saturation temperature. So imagine that we have a very long tank. So let's say this is the tank that we have. In this tank, we have liquid water. So let's say here we have some liquid water. This tank has one inlet here and one outlet. Okay, so let's say stream is entering into this tank or container at temperature of T1, and this tank is long enough that once the stream is leaving the tank, it has a relative humidity of 100%. That means water evaporates from this liquid body to the stream. So these arrows are showing evaporation of water from liquid phase to the stream. So the point is we want to make this tank long enough so that the relative humidity in the exit is 100%. All right. And in addition to these two ports, we have a third port here that supplies liquid water. All right. So from here, we are pumping liquid water at the same temperature as we have here at the outlet. So let's say the liquid water is pumped at T2. Okay, and let's call the mass flow rate of liquid water that we are supplying from here m dot f, m dot subscript f, and once again the temperature here was T1, the temperature is here T2, and the relative humidity is 100%. Now the goal is to obtain the absolute humidity of this stream. That is the purpose of doing all this. Okay, so as I said before, the dry air mass flow rate along this tank or along this channel is constant. That means the dry air mass flow rate which enters from inlet 1 is equal to the dry air mass flow rate that leaves from outlet 2. That dry air mass flow rate does not change. So let's call that m dot a without any subscript of 1 or 2. Okay, so this is the conservation of mass that we have for dry air mass flow rate. I'm going to do the conservation of mass for water as well. Okay, so let's say in the inlet I have water vapor entering, so that is m dot w at inlet 1. Also I have some water here entering, so let's say m dot f, and that is equal to amount of water which is leaving here in phase of vapor. Okay, m dot water at outlet 2. So these two, imagine that the entire tank is our system. So in this system there is one inlet of mass here and another inlet of mass here. So these two are inlets of mass, and this is the only outlet of mass that we have. So the conservation of mass for water says water entering the system from here plus water entering the system from here is equal to water leaving the system from here. But the point is, for this inlet and this inlet, the phase of water is in vapor, but for this inlet, the phase of water is in liquid. But that's fine, because the liquid is also evaporating, we can still consider that. Okay, and this is the conservation of mass for water. Now, what I'm going to do, I'm going to utilize the definition we had for absolute humidity to rewrite this m dot water. Okay, so if you remember, absolute humidity was mass of vapor over mass of dry air. Now I can write this based on m dot v over m dot a. So this m dot v is the same as m dot w here. Don't worry about the subscript here. We have v here, we have vapor. Both of them are referring to as water vapor. Maybe it was better if here I was using m dot v, but both of them are the same thing. So that means I can find this based on m dot a multiplied by absolute humidity. So in the inlet, I have absolute humidity of omega 1. In the outlet, I have absolute humidity of omega 2. So let's say m dot v or m dot water at the inlet, water vapor at the inlet is going to be omega 1 m dot a. Okay, so this replaces this one. Plus m dot f, which is this one, is equal to omega 2 m dot a. Okay, now I can solve these for m dot f. M dot f is going to be equal to m dot a multiplied by omega 2 minus omega 1. Okay, so that was the conservation of mass that I have done to obtain m dot f. For the next step, I'm going to apply the energy balance on this system. Once again, speaking of system, the entire tank is my system. So for energy balance, I have one inlet here and another inlet here, and I have one outlet here. So the energy balance says E dot in is equal to E dot out. Okay, the reason behind this is because it's an open system, so there is no energy stored within the system. So whatever energy enters the system is equal to the energy leaving the system per unit time. Okay, now energy entering the system is in form of mass. Okay, so that means my E dot in is going to be m dot a h1 plus m dot a omega 2 minus omega 1 multiplied by hf2, which is equal to m dot a h2. Okay, so what I'm doing here, I'm saying m dot dry air multiplied by enthalpy at the inlet plus the whole thing here is my m dot f. M dot f multiplied by enthalpy of liquid water, which is entering here, is equal to mass flow rate of dry air leaving the system multiplied by enthalpy at the outlet. Okay. Also, one thing that I know is H1 itself, I can divide the whole thing by m dot a. So H1 plus omega 2 minus omega 1 multiplied by hf2 is equal to h2. So this line came from dividing all terms by m dot a. Okay, now this h1 itself is in fact equal to ha plus omega hg. We showed that in the previous pages. Okay, so this is enthalpy of the atmospheric air here, which includes the enthalpy of dry air plus the enthalpy of water vapor. So these two H's are the same. Okay, that means instead of H1, I can write the right hand side. Okay, and the right hand side for HA is specific heat multiplied by temperature. So basically, instead of H1, I can say CPT1, which is this one, plus omega 1 Hg at condition of inlet, or let's say Hg1. So the whole thing here is my H1. So this CPT is HA because this is the enthalpy of dry air, specific heat multiplied by temperature, and this is the second term. Plus omega 2 minus omega 1 multiplied by HF2 is equal to H2. And once again, I do the same concept that I had here. H2 is equal to enthalpy of dry air plus enthalpy of water vapor. So it's going to be Cp T2 plus omega 2 Hg2. Okay, now I can solve this equation to obtain omega 1. And omega 1 is equal to Cp T2 minus T1 plus omega 2 HFG2 over Hg1 minus HF2. So if I solve this line for omega 1, this is what I will obtain. Okay, so this equation gives me omega 1, but in this equation I have omega 2. But the thing is, for omega 2, I can use the equation that we had before. So if you remember previously we had, I'm trying to find that equation. So if you remember previously we had this equation. Now I can use this to find omega 2. The reason is here for outlet 2, my relative humidity is 100%. So that means I can utilize this equation to obtain the omega 2 because my relative humidity is 1 or 100%. The same thing here. So based on this, I can develop equation for omega 2. Omega 2 is equal to 0.622 Pg2, right, over P2 minus Pg2. So basically, this omega 2 that I have in this equation is something that I can easily obtain. Now, I'm sorry, I think you didn't see that. So the only thing that I added was this equation. Omega 2 is 0.622 Pg2 over P2 minus Pg2. And the point is this omega 2 that I have in this equation is coming from here. That's it. Now, here I have T1 and T2, right? These T1 and T2 obviously are, so let's say T1 for instance, T1 is the temperature at the inlet and T2 was the temperature at the outlet, okay? But they do have a name. So we call T2, we call it wet bulb temperature, and T1 is called dry bulb temperature. I will discuss why we are calling them these two names. Okay, the reason that we call T2 a wet bulb temperature comes from the fact that we can measure that temperature if we have a thermometer. So let's say this is a thermometer, and in this thermometer, in the bulb part, we have a wet wick or wet cotton, let's say, attached to the to the metal part of the thermometer, and there is a flow of air. So the temperature that we measure by this thermometer is the wet bulb temperature as we have here. The dry bulb temperature is the temperature that a regular thermometer is reading basically. So let's say if this is a thermometer and there is no wet wick around the bulb, so the temperature that we read here is the dry bulb temperature, and this one was wet bulb temperature. All right. So a more practical way to obtain the temperatures is basically using something like this. Let me show you what we have in the textbook. There is something called Sling Psychrometer, And that device gives us these two temperatures. This thing here. So if we use this Sling Psychrometer, what we have here is two thermometers side by side. For one of the thermometers, we have a wet wick around the bulb, and by rotating this psychrometer, we are reading two different temperatures, a wet bulb temperature and a dry bulb temperature. Okay, so this dry bulb temperature is exactly T1 that we had in the discussion, and the wet bulb temperature is T2.